All right, so it's Friday, and I have decided I'm going to do something that's really, really fun. So I'm going to go through the booklet, the Foundation Mathematics booklet that Mr. Patrick made for us, and do all the maths and show you the best way of doing it. Now, it is a fairly decently large document, so you may at some point get a little bit bored, want to disappear, go look at other things. By all means, do that. You can come into this video at different sections, and I have figured out the way of making chapters. So at some points I'm going to go through and label where each question is, 23, 19, 20. So if you're struggling with one particular question, you can look in the links or the information thing down below at some point in the future, and it will show you where each of the questions are. So the way I've set this up, I've got the questions on the right-hand side, and I've got the equations list that you're allowed to have next to you in the exam beside you as well. So I'm going to be using it pretty much the same way you will be. So let's get going. Woo! Now, depending on whether or not my voice dies, this could be broken into two parts, but let's see. So question 1, figure 6 shows the student results, I assume from some kind of experiment. We have the mass of a metal block of 0.92 kilograms, the power of the heater 50 watts, starting temperature 20 degrees Celsius, finishing temperature 54 degrees Celsius, and total time 300 seconds. That's 5 minutes if you're not a physicist, but there you go. Now we have to use the data in figure 6 to calculate a value for the specific capacity of the metal. Use the equation specific capacity equals power times time divided by mass times temperature rise. So first thing I'm going to do is I'm going to collect all of my terms. I'm going to write down that my mass is equal to 0.92 kilograms, that the power is equal to 50 watts. The starting temperature was 20, the finishing temperature was 54, so the difference between those is 34 degrees Celsius. They've asked for the temperature rise, so that's the one I've got to include. They give us two temperatures there. I know that the symbol for that is delta theta, and I'm going to give that as 34 degrees Celsius, and the total time t was 300 seconds. Now they've happily written us the equation there so that we don't have to. So we're going to write down that specific heat capacity is equal to the power, 50, multiplied by the time, 300 seconds, and then divided by the mass, which is 0.92. I'm going to multiply that by the temperature rise, 34 degrees Celsius. Now I'm actually going to use my calculator for all this, because it will give you a more realistic idea about the amount of time that you should be spending on each question. Oh, and I just messed that up, so it's going to take me a little bit longer. But remember, if there's time to do it again, there's also time to do it right the first time. Now, it's not asking me for any significant figures or anything, so I'm absolutely fine in writing down the full answer that I've got, 479.5396419, and then I am going to round that down. So this is giving me 2 decimal points, so I'm going to give this in 2 decimal points. I write 479.54. Now, obviously, you lot are going to be able to do this a little bit neater. I'm going to struggle a little bit because I'm using a mouse. All right, so we've got another question here. Let's have a look at what we got. Cyclist is riding a bike at a steady velocity of 12 meters per second. The cyclist and bicycle have a total mass of 68 kilograms. Mass is 68 kilograms. The cyclist starts to cycle again. The cyclist does 1,600 joules of useful work to travel 28 meters. Calculate the average force the cyclist exerts. Now I'm going to collect all of my terms. Steady velocity, so v is equal to 12 meters per second. You will have to get used to knowing which each of what all these things are. So you need to know that mass is m. And you need to know that if I see a J, then it's going to be energy, 1,600 joules, and travel 28 meters. That's going to be a distance or a height. I'm going to write down it's a distance because unsure if normal bicycles go upwards. And I'm looking for force as well. I don't know how many newtons. Now, I know my equations, but we're just going to go over and have a little check of here. Can I find an equation that links force and energy and distance all together? Do we have one there in front of us? Here it is. Energy, force, distance moved in the direction of the force. E is equal to F times D. So I'm going to go back and I'm going to write my equation. I'm going to write it down so the examiner doesn't mess me around. If I make a mistake later on, the examiner knows where I started and they can possibly give us marks. They're asking for force, so I need to rearrange this equation. F is where I want it to be. I'm going to move D from the top of the line to the bottom of the line. I'm going to move D from being on top to being on bottom. I'm going to divide across by D. E divided by D is equal to F. And then I'm going to put my numbers in. I have energy of 1,600 divided by the distance, 28 meters, which will equal the total amount of force. 57.14. 57.14286. But because there's no issues here, there's no decimal points here or anything like that, I'm just going to return it as 57.14, just to make it a little bit more tidy. There's a piece of music called The Flight of the Bumblebee, and it goes. That's how that one goes. And yes, I am taking. If anybody would like to sign me to a recording album, please do so. Let's have a look at the numbers. We don't need to worry about the flight of the Bumblebee. We just need to look at the numbers. It takes 4 minutes to play. During this time, a bee flies 1,608 meters. Calculate the average speed of the bee. So same thing. Time is equal to 4 minutes. Now, when I see minutes, I think that's not good. I want to convert that to seconds because that's the base unit for time. I'm just going to look over here at my units, and yes, they do want me to do that. So 4 multiplied by 60, 240. 240 seconds of time. He flies for 1,680 meters. Now, that could be up or down or across or whatever. I'm still going to make that as a distance, 1,608 meters, including my units. Calculate the average speed. Speed is equal to, I don't know, meters per second. Let's have a little look at my sheet over here. Is there one there for speed, distance, and time? Distance, speed, and time. Distance traveled equals average speed multiplied by time. So I'm going to write down my equation. And I'm going to stop my voice squeaking quite so much. Distance is equal to speed multiplied by time. It's asking for speed, so I need to rearrange this equation, divide across by t. D divided by t is equal to s. Or you can just think, I'm going to move that t underneath the line. That's what it looks like. 1,608 divided by 240. 1,608, oh, pardon me, is equal to speed, because we don't like hanging numbers. We don't like things that are without an equals to sign. It gives me an answer of 6.7 meters per second. Ooh, isn't this fun? A student calculates the volume of the block, with another strange and aberrant block, as 13 meters cubed. She finds the mass of the block is 100 grams. Calculate the density of the block. Use the equation, and it would say something here like density equals mass divided by volume, but it doesn't there at the moment. So I'm going to collect my terms. The volume of the block is 13 centimeters cubed. The mass of the block is 100 grams. Now, centimeters cubed? No. The base unit for that will be meters cubed, and the base unit for this will be kilograms. So I've got to convert, don't I? Look over here. It's asking me for the units to be in grams and centimeters cubed, so I can keep those numbers the way that they are. The density is equal to, I don't know how many, grams per centimeter cubed. So I've written my equation. I should write the density is equal to 100 divided by 13. Density is equal to 7.692. I'm going to give that a 7.7. Now, I've given my number here. I've given my number here. They haven't told me about any significant figures, so both those answers would be utterly accurate. Figure 2 shows an energy transfer diagram for a steam engine. Choo-choo. The diagram shows the amount of energy transferred each second by the steam engine. Energy input is 2,000 joules. Remember, useful energy goes to the side, and just like if you're going to the toilet, the wasted energy goes down. Useful energy output is 160 joules. The wasted energy hasn't given me a number. I bet that's going to be something I need to find. Yes, look at that. Calculate the amount of wasted energy. So to do that, I need to figure out how much this number is. Remember that energy cannot be created or destroyed, so the total amount of energy into the system will equal the total energy out of the system. The energy in will be equal to the useful take away the wasted. No, that's stupid. Useful plus the wasted. Whoopsie. The amount of energy in will equal to the useful energy plus the wasted energy. In minus useful will equal wasted. 2000 joules. Take away the useful energy, 160 joules, will equal the wasted. And there's no equation for this, it's just something you have to figure out. 2000 take away 160 on my calculator is 1840 joules. Calculate the efficiency of the steam engine. Now for this, I am going to use an equation. It isn't given to me there, but let's have a look over here. Let's see if they give me the equation for efficiency. Don't know if they do or not. Oh, there it is. Look at that. Hello, old friend. Useful divided by total. Oopsie. Calculate the efficiency of the steam engine. I'm going to have to collect my terms because it's useful divided by total. Useful divided by all the energy going in. I know that my useful energy is equal to 160 joules. My total energy is equal to 2000 joules. My efficiency, I have no idea. The equation is efficiency, useful divided by total. Efficiency is 160 divided by 2000. My efficiency is going to equal 0.08. Now, it's not asking it for in percentages, so I can leave it as a decimal point, but if I needed to, I could multiply that by 100 to get the efficiency. That says 106. Ignore it. Die. Multiply it by 100 to get the total efficiency. Shot put is an Olympic event. Ooh, stop moving. Shot put. A shot is a heavy ball. An athlete throws the shot as far as possible. A sports scientist analyzes an athlete's throw to help improve their performance. In one throw, the shot continues to rise by another 1.3 meters after it leaves the athlete's hand. The mass of the shot is 7.26 kilograms. Calculate the amount of gravitational potential energy gained by the shot. So let's have a look. It's rising 1.3 meters, so we'll say that h is equal to 1.3 meters. We'll say that the mass is 7.26 kilograms because it's given to us, and it's asking me to find the gravitational potential energy. I know energy is measured in joules. So it's asking me to find GPE. J hasn't given me an equation. Let's look at my sheet. Whoa, let's not do that. Is there an equation that links gravitational potential energy, mass, and height? Ooh, well, we've got this one. Gravitational potential energy, mass, height. But there's a weird little thing in here. They didn't give me a number for that, you say. Well, the number for gravity is the same everywhere. Gravity is 10 newtons per kilogram. So I'll write out the equation. Remember this little triangle here is delta, stands for change. And I'll put my numbers in. Sneaky of them not to give us that number, hey? 7.26 times 10 times 1.3. Oh, deleted that. That's clever. 94.38 joules. And I'm definitely allowed to put the decimal points in there because there were 2 decimal points in there. A ball has a mass of 0.04 kilograms. Calculate the change in gravitational potential energy when the ball is lifted through a vertical height of 2.05 meters. Oh, that should be h. All right, and again, it's giving me these things. What is the equation if I've got mass, gravitational potential energy, and height? Oh, it's the same equation. So I'm going to write down that gravity is equal to 10. Well, sometimes they'll tell you to use 9.8, but if they don't, then you can just use 10 because it's easier. All right, my equation. EP and GPE are the same thing as far as they're concerned. I'll use both just to get you used to them. 0.046 times 10 times 2.05. And that is 0.943. 943. And again, 3 decimal places is fine because we have 3 decimal places there. The ball is released. Calculate the kinetic energy of the ball when the speed of the ball is 3.5 meters per second. 3.5 meters per second. Now, it's going in one direction because I'm throwing it, so I'm going to say that's my velocity. And it's asking me to find the kinetic energy. But sir, how do we do that? We only have one number. Well, let's have a look at what the equation for kinetic energy actually is. And there it is. I can see it already. Kinetic energy is equal to 1/2 the mass times the speed squared. K is equal to 1/2 mv squared. So this is the equation I'm going to have to use. Kinetic energy is equal to 1/2 times mass times v squared. I have my v. Where is my m? My m is here. The m has already been given to us. Sometimes you need to use numbers from part 1 to find the answer for part 2. Mass is equal to 0.046 kilograms. I'll write this down, substitute my numbers. 1/2 times 0.046 times 3.5 squared. Don't know why my voice is cracking. Possibly because I've had a long day of shouting grumpily and losing my temper. So that's probably why. Put all those numbers into my calculator. I get an answer of 0.28175, 0.28, both are fine. Question 11. A student investigates the motion of a trolley along a horizontal runway using the apparatus in figure 2. Trolley, card, runway, block of metal, pulley, light gates. How exciting. A trolley is attached to a string passing over a pulley. A block of metal hangs on the edge of the string. Each light gate measures the time it takes for the car to pass through the gates. So I'm going to get one time here. I'll call that T1, and this will be T2. When the trolley is released, it moves along the track. A computer measures the time it takes for the car to pass between each light gate. The card took 0.8 seconds, so there's a time there, equals 0.08 seconds, to pass through the first light gate. The width of the card is 5 centimeters. Width is weird. So I've got a card here, and we're saying that the width is that amount of Now, we never looked at anything for width, but I'm going to write down that width. I've got no symbol for width because I've never given you one. I'm going to write down that it's equal to 5 centimeters. Now, centimeters. Do we want centimeters? Look at the units. No, we do not. They want meters. So we divide that by 100. 0.05 meters. Calculate the average speed. Speed, width, and time? But sir, we don't have an equation for that. No, but what equation do we have? Now, I'm not going to move over and back quite so often, just because I was getting a bit seasick. But I know that I've got an equation. Maybe I will do so for this one. So what did you do with your Friday? Well, I sat in my office and I spoke to myself about maths. Did you enjoy it? Yes. Let's look here. Let's look at any of these equations that we might possibly be able to use. Okay, so we got distance traveled, average speed and time, acceleration, force, mass, weight, efficiency, wave speed, work done, power done, energy transferred. Right, none of those are helping us. Apart from maybe this one. Distance traveled, average speed and time. Because you can either have an object moving from point A to point B, or you can move an object from point A to point B. Yeah, we could do that as well. Or we could have our object there, and we could measure the point A to B. Oh, why aren't you doing it? Come on, everyone else did it. There we go. We could measure the time it takes for that object, instead of going from A to B, just how long it would take that object to pass B. What distance, what amount of thing went through B? So rather than my object going from A to B, we can just see how long it takes this little piece of card to pass point B. What is the distance and what is the time that it takes this object to pass point B? How wide is it? How long does it take? And we'll be able to find speed. So maybe instead of thinking of this as width, we'll think of this as distance. Then we'll be able to find the answer. Speed is equal to distance divided by time. Speed is equal to 0.05 divided by 0.08, giving me a number of 0.625. Or I could do, if I wanted to, 0.63. That's your answer. Now another trolley passes through the first gate at a velocity of 0.72 meters per second. So at gate 1, we had a velocity of 0.72 meters per second. The trolley passes through the second gate at a velocity of 1.1 meters per second. So the second velocity is 1.1 meters per second. We can use little subscript numbers like this to show difference. So if we've got two mentions of velocity or temperature or mass or whatever, well, not mass because that won't really change, but what we can do is use subscript 1s and subscript 2s to say that this is the first one and this is the second one. The time it takes for the car and the trolley to travel between the two light gates is 0.53 seconds. So I'll say that my time is equal to 0.53 seconds. Now it's asking me to calculate the acceleration. I have no idea meters per second squared. What equation links v1, v2, t, and a? None. But there is an equation that says acceleration is equal to v minus u divided by t. The end velocity, or the second velocity, divided by the start velocity, or the first velocity, divided by the time taken. 1.1 minus 0.72 divided by 0.53. So my calculator, I'm going to do open brackets 1.1, take away 0.72, close brackets, a over b, and then I'm going to write my time, 0.53. Then I'm not going to have any bid mass errors. My acceleration is 0.7169811132 meters per second. I don't like that very much, so I'm just going to bring that down to 0.72. Now, it doesn't ask for significant figures, but usually, if you've got 2 decimal points in your data, you give 2 decimal points in your answers. An earthquake causes a sea wave, and nobody waved back. It was very sad. Ha ha ha. The sea wave travels 26,400 meters in 2 minutes. So, one number there, one number there. It travels a distance, 26,400 meters, in a certain amount of time, 2 minutes. That is the same as 120 seconds, because I multiply by 60. What is the speed of the wave? I don't know. Use the equation, speed is equal to distance divided by time. Speed is equal to 26,400 divided by 120. This gives me an answer of 220 meters per second. Look at that, folks, 4 down. Only about 20 to go. Another cyclist travels 1,200 meters in a time of 80 seconds. Calculate the average speed of the cyclist. Speed equals distance divided by time. I'm going to write it a different way because we've seen this before. 1,200 divided by 80. My answer is 15 meters per second. Figure 13 shows a drone. A different drone has a mass of 4.5 kilograms. The drone rises from the ground to a height of 20 meters. Calculate the change in gravitational potential energy. GPE equals I don't know how many joules through a height of 20 meters. Oh, I already have that number. Gravitational field strength is 10 newtons per kilogram. Oh, they're being nice. They're reminding us of it today. EP is equal to m times g times delta H. EP is equal to 4.5 times 10 times 20. 900 joules. State the useful amount of work done by the blades as the drone rises through 20 meters. Well, if it's gone from 0 meters up to 20 meters, then the useful amount of work done is the force multiplied by the distance. And to find the force, it is the mass times the gravity, and the distance it's traveled is the height. The work done and the gravitational potential energy will be the same, so I can just do 900 joules. It takes 4 seconds for it to go up 20 meters. That's very fast. The time is 4 seconds. The distance traveled was 20 meters. Calculate the power in this amount of time. But there's no equation for distance, time, and power. But there is an equation if we look at the sheet. They like to do this. They like to give you a, like I said, sometimes they'll hide the numbers that you need in the previous question. They have got power, work done, and time taken as an equation. So let's have a look. The work done, we've already worked out, was 900. Now, don't panic, okay? If you wrote the wrong answer to this question, let's say you wrote 10 here, and you used 10 in this section, you would still get full marks for this question. You get no marks for that, but full marks for that. So don't panic if you get one wrong. You only lose a mark once. The equation we were given was energy divided by time. It's asking me to find power, so I just have to substitute my numbers in. That's 900 divided by 4. Gives me an answer of 225 watts. The mass of a piece of copper is 0.058 kilograms. The volume of the piece of copper is 6.5 times 10 to the minus 6 meters cubed. Calculate the density of the copper. Density equals, I don't know, kilograms per meter cubed. And that's the units that they want, so I'm all good. The density is equal to the mass divided by the volume, which is 0.058 divided by 6.5 times 10 to the minus 6. I'm going to put that into my calculator. 0.058 A over B, 6.5 times 10 to the y to the x, that button in the top left, and then minus 6 underneath 3, giving me an answer, 8923.076923. 8923. Decimal points down to 3. Well, actually, lots of decimal points there. Yeah, I'll leave it as it is. I'll do both those things. I'll write both those things down. And I'll definitely get the marks because it didn't say we use any significant figures. An aircraft waits at the start of a runway. The aircraft accelerates from a speed of 0 meters per second, so velocity 1 is equal to 0 meters per second, to a speed of 80 meters per second. Velocity 2 is 80 meters per second. Here, acceleration of the aircraft is 4 meters per second squared. Calculate the distance traveled by the aircraft while it is accelerating. They're very nicely giving me my equation. The distance is equal to v, which is the end velocity. Think about this. And I'm going to P, Q, R, S, T, U, V, W, X, Y, Z. Which one comes first, U or V? U comes first, V comes second. So V is the end velocity, U is the start velocity. My second velocity was 80 meters per second. Squared, take away 0 squared, divided by 2 times 4. So I'm going to do 80 squared. Actually, I'm not. I'm going to open brackets, 80 squared. Take away 0 squared, even though that doesn't make any sense. A over B, 2 times 4, is going to give me one answer. The distance it traveled was 800 meters. The kettle contains 1.5 kilograms of water. 1.5 kg. The kettle is switched on. Calculate the energy needed. Oh, I need to find the energy. What is that? I don't know. To raise the temperature of the water by 5 degrees Celsius. I know that change of temperature is equal to 5. That's 50. Come on, man. Specific capacity of water is 4,200 joules per kilogram degrees Celsius. What is the answer? I need to use this equation. Now, in this equation, delta Q is the same as delta E, change in energy. So I'm going to write down that delta Q is equal to my mass, 1.5, times C, 4,200, times delta theta, which is 50. Delta theta is equal to 315,000 delta theta. No, thank you. Delta Q. Now, what I did there was a common sense check. I saw that I'd written there delta theta, which means temperature. And I got 315,000. What? I'm talking about the wrong thing. This is the change in energy. And that does actually make a little bit of sense. Makes a lot of sense. If you need 4,200 joules to make 1 kilogram go up by 1 degree Celsius, if I've got 1.5 kilograms of water going up by 50 degrees Celsius, then I'm going to need a much bigger number than that. So I did a check myself before I wrecked myself. I did not wreck myself, in fact, so well done me. The amount of energy needed to bring the water to boiling point is 670,000 joules. The kettle is a power rating of 3,500 watts. Calculate the time it takes to bring the water to the boil. In seconds. Do you want me in seconds? Yes, they do. Power equals energy divided by time taken. Fun little fact, if you want to rearrange this equation to make T the subject, all you have to do is swap it with the term that's by itself. And we get 67000 divided by 3500, giving me the answer. Time needed to bring the water to the boil, 191.43 seconds. Let's have a look at that. 670 joules, power rating of that, power rating of that. Power is energy divided by time. Rearrange this equation. Time is equal to energy divided by power. Definitely put the energy there. Yep, so that seems a long time to boil a kettle, but there we go. 191 seconds. What's that? 2.5 minutes. Need to buy a new kettle. Model train is a mass of 8 grams, 8 kilograms. Travels at a speed of 1.5 meters per second. Calculate the kinetic energy of the model train. EK equals, I don't know how many joules. So instead of speed, we're going to write velocity. EK is equal to 1/2 times mass times velocity squared, because I'm going to write down my equation every time. EK equals 1/2 times 8 times 1.5 squared. Really important that we square that number. It's a very common mistake to not. 0.5 times 8 times 1.5 squared equals 9. My kinetic energy is 9. Wire in a circuit carries a current. I equals 0.9 amps. I remember I, current, I stands for intensity. How intense is the flow? And actually, it was in French because it was a French chap who discovered intensité. What is the intensity? How fast is that current flowing? What is the rate of movement of coulombs through my wire? Calculate the quantity of charge. The Q of charge equal to I don't know how many coulombs, because one electron is useless, but a packet of electrons is useful. Flows through the wire in 50 seconds. Go find my equation. Charge is equal to current multiplied by time. Charge is equal to 0.9 multiplied by 50. That is 45. One electron by itself is useless. Packet of charge is called a coulomb. The unit of charge is C. Wave has got a frequency of 15 hertz. Its wavelength, lambda, is 125 meters. Lambda is this letter. It stands for wavelength. It can also be called sheep daddy. My year 9s came up with that, and it's hilarious. Calculate the speed of the wave. Now, waves travel in one direction only, so I'm going to say the velocity of the wave, and I don't know how many meters per second. Velocity is equal to frequency multiplied by wavelength. Velocity will be then 15 hertz multiplied by 125 meters. 15 hertz multiplied by 125 meters, 1,875 meters per second. A different water wave has a wavelength, lambda, of 0.25 meters and a frequency of 1.5 hertz. Calculate the wave speed. Because this is a wave, I say velocity, because it's going in one direction, so it's a vector. Velocity is frequency times wavelength. Velocity is 1.5 times 0.25. 1.5 times 0.25 is equal to 0.375. Wavelength of that, 1.5 of that. Okay, that seems correct. And my units all match up. Lovely. Oh, what are we doing? Okay, sorry folks, give me 2 minutes. Okay, I've obviously pressed something, haven't I? Okay, no need to panic. We're just going to zoom back in. There we go. Sorry about that. If anybody there got seasick, I'm really sorry. The car is moving at 90 kilometers per hour. So we're going to say its speed is 90 kilometers per hour when the driver has to stop. Calculate the thinking time of the driver. Time is equal to, we don't know how many seconds. Use the equation time is equal to distance divided by average speed.